All right, yesterday I built a kit, an MK136. It's an audio amplifier with microphones, and it did come with a schematic. And I thought we'd talk about the schematic today. I sort of wanted to bring up some comments and maybe some ideas. So here it is. I'll show a better picture. And it's just two channels. Each channel is exactly the same. So we'll just talk about one channel. And it's just a microphone and an amplifier, and that's it. It's just one microphone and one op amp, and then a bunch of biasing and stuff to make it work, okay? So let's talk about that circuit. Let me redraw it. Okay, let's first talk about this resistor right here. These microphone modules actually have an FET inside of them, and they're amplified. So there's actually a little bitty amplifier inside these microphone modules. And they require power to work. And so this resistor supplies power to that circuit, okay? And so you can almost imagine the way that I have it drawn here. This is kind of a microphone symbol, but this could be like an FET or something, right? And so you're biasing it, and as it goes up and down, you're getting a current change here, and you're getting a voltage change out here. Well, that's exactly how it works. There's actually an FET inside and all that kind of stuff. So let's see, what kind of value do they use on that? Yeah, they used to 10K. All right, so this is 10K. So that supplies the power. I think 5K is standard? I don't remember now. I think Sony invented it way back in the day, but a lot of microphones require this this voltage, and a lot of units, like I use this Sony digital recorder to get my audio, and it has a microphone input, and it has this resistor in it, so it's very, very similar to Phantom Power. Phantom Power is a 70 volt system. It has 70 volts coming in here, but obviously you would blow out these little guys. But yeah, it's just 5 volt. It's like 3 to 5 volts operate these things. So anyway, okay, talk too much about that, but that's why this resistor is here. Now, because you have a DC bias here, you're only interested in the change, not the absolute value. You're interested in the relative value. So that's what this capacitor does. It just sends through the audio. Okay, now. This part of the circuit is just a non-inverting amplifier, right? You go in the positive input of the op amp, and you have some type of resistor divider string here that supplies the amplification. This has a capacitor in it to slow things down. And let's see here. Then this may be at some DC level. So it's AC coupled to the outside. And then over here is the earphone, okay? And so you put your earphone over here. This is a low value. This is like 8.2 ohms, and I think this is 1K. Yeah, this is 1K. So that's the output circuit, and this is a really heavy capacitor here to let through current. So they have added a whole bunch of extra things in their circuit. All right. So let's take a look at their circuit. Let's see, I really need to get my camera down a second. Okay, that's better. So we come in here, we go through the capacitor, we go through this resistor here, which is just the volume knob, right? You're just taking some percentage of the signal and going to amplify that. Now, then they go through a second capacitor, and they go through this totem pole push-pull thing here, right? So it's 220K, 220K. Well, that sets a midway voltage for this amplifier. This op amp is running single-ended. It's ground to plus whatever. And so it will not operate to ground. You need to put it somewhere in the middle. Well, this puts it somewhere in the middle, so that's the biasing to put it somewhere in the middle, okay? And then the bottom ground also needs to be somewhere in the middle. It can't go to ground. It has to be whatever this value is. It needs to be somewhere in the middle. So this capacitor averages this. So whatever this voltage is here gets duplicated on the minus. There's a 1K, which is pretty low impedance. That keeps this thing charged up to basically the same voltage as this. And so it's a way for them to operate this thing with a single-ended supply. Well, let's talk about maybe removing some components, all right? So you can see in mine, I have removed a lot of components from that one. And if we had a virtual ground, we'll call this virtual ground, okay? Virtual ground, my pen is running out of ink. Then this circuit would work, okay? All right, so this value here could never get bigger than the virtual ground. So let's say that this is V, our virtual ground is, let's say, V over 2, okay? And so this would keep this op-amp happy, and then the ground system, these two grounds would be basically identical. They'd both be virtual ground, all right? So it gets rid of this capacitor, it gets rid of these two resistors, and it gets rid of this capacitor by having a virtual ground, which means it's duplicated, so we're getting rid of 4 components over here as well. So we're getting rid of 8 components by doing it that way. So how do we generate a virtual ground? Well, I thought, well, we already have an LED, right? So here's our LED, and we're going to turn it on. That's what we want that LED to do, turn on when we turn the voltage on. Well, guess what? That would create like a 1.75 volt voltage here, and we can call that virtual ground. And then that plus 1.75 volts could be our virtual ground, and then we could send it around to everything else, right? So in good virtual ground systems, you generally have a emitter follower or an op amp or something that could drive that virtual ground. You have an active virtual ground. Since we don't have that, we could reuse that 470 microfarad capacitor that comes into this circuit. There's one right here, 407. Now we have a battery powered supply. I don't know why you need a big capacitor when you have batteries, which are the perfect capacitor. So I'm not quite sure what that one does. So we're going to reuse it. We're going to move it over here, and we're going to use it to make our virtual ground real stiff, a very, very low impedance virtual ground, because it's going to store a lot of energy here in this 470 microfarad capacitor. So anyway, it's a circuit for discussion. Leave comments below. You can see that we've gone from a somewhat complicated circuit to a more simplified circuit, and so yeah, give me your thoughts about it. One of the things about these, although this is a Belgium kit, I call these Chinese kits, is reduce the chip count, make the chip count as small as possible to do something. Yeah, I've reduced it by at least 8. So yeah, give your comments.